So I'd like to sort of go over this question here, which I think is a very good demonstration of molarity and dilution problems, and really how this stuff can sort of get intertwined, and how one would need to navigate through these types of questions to eventually, hopefully, get the right answer. So in this question here, it says that zero point 0.8, a zero point 0.8 molar HCl solution was diluted to a final volume of 500 milliliters. And we have two questions here, part A and part B. And the first part essentially says if the new concentration is 0.20, if the new concentration has a molarity of 0.20, what was the original volume of the solution? We'll sort of tackle the other part later, but the first part I think is quite important to even get to the second part. In fact, the second part is somewhat trivial, but the first part, if you're really not able to process what the question is asking, really the best way to tackle the problem is to think about it in terms of pictures. So really, I mean, if you think about it, we have a container, and within that container, we have a solution, and the solution has what we're told in the question at least is that the solution has a molarity, right? The solution has a molarity of 0.8 molar. So the idea, and this is of course HCl. The idea is that we don't know how much volume that this solution basically consists of, but we know that the molarity is 0.8. In other words, every liter, we don't know the amount of liters or milliliters, but we know that for every liter, there are 0.8 moles of HCl. So, sort of processing the question further, it says that, this particular solution was diluted to a final volume of 500 milliliters. So, clearly what we've done, and this is sort of the first situation, and the second situation essentially states that we've diluted it, and so we've essentially added more water to this solution, thus rendering the molarity. Of course, if you were to add more water, the concentration of HCl would essentially decrease. You'd have less HCl. And the idea then would be that the molarity would actually have to sort of correspond to that. So your molarity in the second situation, it says that you've diluted it to 500 milliliters, and the molarity is now 0.2 or 0.20. You could call it 0.20, but the molarity is now 0.20, right? And unlike the first scenario, this one actually tells us the amount in terms of milliliters, right? Not liters like we would want, but milliliters. It says that it essentially states that the diluted solution in total is 500 milliliters. Right. So the second one is really cool because it not only does it give us the molarity, but it also gives us, unlike the first, it gives us the milliliters in total. And so the first part of this question really is sort of concerned with, well, we've given you the molarity after it's been diluted, and we've given you the milliliters that diluted solution is in its totality. But what in fact would be, if given that information, what in fact would be the sort of the quantity in milliliters, or of course liters, you could express it as liters, but what would the volume be of the original solution, right? And so it's tricky, it really is. But really the way to go about it is to understand that if you have, whenever you're talking about molarity, or sometimes the word will be disguised with another word, which is concentration, you're really talking about the same thing. And nearly always the formula for that is, this is of course the sign for molarity, but the formula for that would be you would take your moles of solute, which is the thing that you are in fact dissolving, over your liter solution, right? And the idea is that this formula is essentially exclusively for the use of liters. In other words, if this produces anything, right? If this produces anything, it will produce liters, right? So this is always in terms of liters. If I put any quantity here, even if I put a milliliter based quantity, it would essentially produce liters, right? So that is something that we'll have to consider later on, but it's an important point to note. If you had milliliters and you get an answer, that answer is not going to be in milliliters. It will essentially go through a process where it will be in terms of liters. So it's exclusively for liters, and with that in mind, sort of returning back to the original question, what is the amount in terms of liters for this particular solution before the dilution happened? So we know that this stands true, and the other fact about this formula is that if you have one of the three, right, within a particular scenario, then you can in fact solve for the missing part. It's kind of like the Pythagorean theorem almost. If you have moles solute and you have liters solution, then you can get the molarity. If you have the molarity and moles solute, you can get the liters. If you have the liters and the molarity, you can get the moles. And so that's how that works. But we need at least two known values to get the last unknown value. And so, I mean, really, if you think about that intuitively speaking, if we have in the first situation we have the molarity, if we either had the liters, or of course if we had the milliliters, but we would have to take into account that it would be changed to liters. But if we had the liters or the milliliters, or if we had the solute, right, then we could we could find out the other. Now, for this particular case, we want to find out the liter quantity. So we would need the molarity, and we would need the moles of the solute. So it then becomes quite apparent that if we solve for moles solute, then we would both have the molarity and we would also have the moles solute. And then, of course, we would be able to solve for liters in terms of the original solution. So sort of as an intermediate digression, it becomes apparent, why don't we try to figure out how many moles are in this particular quantity? And of course, that would allow us to solve for liters, but a very important point to note is that if you were to calculate how many moles are in this container, right, however many liters or milliliters that is, if you were to calculate the moles there, and if you were to calculate the moles here, you would essentially get the same amount of moles. Now, why is that, right? Why does that work? And the fact is that if you dilute something, if you just add more water into the container, you still have the same amount of moles of solute, right? I mean, if you had sugar and you dissolved it in water, or salt and you dissolved it in water, just because you add more water doesn't really change the fact that you have the same amount of solute, which in this case would be salt or sugar as another example. So calculating the solute, even if you do it with this information, in fact, you would need to do it with this information because you don't really have enough information in this guy to get mole solute. But if you calculate the mole solute, at any rate, it will be the same here and it will be the same here. So calculating the amount of moles using this information would be the same thing as calculating the amount of moles had we had the milliliters in this solution. So, now as a sort of an intermediate digression, as I said before, is to calculate moles solute in either solution, right? In either solution. Now, the one that we have chose sort of to calculate the moles solute from is this solution, because this solution gives us everything we need to calculate moles solute, or HCl, in terms of moles. And it's given us the molarity and it's given us the milliliters. And that becomes helpful because what we can do is we can use sort of a stoichiometry styled conversion factor in order to get from milliliters to moles in HCl in this particular case, right? So what we could do then is we could say we have 500 milliliters. And if you convert that milliliters over to liters, right? If you were to say 1,000 milliliters, and this is of course of the HCl solution, right? This is also of course of the HCl solution. So if you had 1,000 milliliters over 1 liter, right? Because we know that's a conversion factor for converting from milliliters to liters, then effectively you'd get how many liters that is. But you want to extend this further to calculate how many moles are in this particular container, this container, not this container just yet, but this container, because of course calculating the amount of moles in this container would be similar to calculating the amount of moles in this container, since the amount of moles don't change. So effectively what we would do in this point is we would want to have a conversion factor that would be relevant to this particular container, which would allow us to put liters on the bottom and moles solute on the top. And what that would do for us is it would allow us to cancel liters, which is of course what we're left with on this side, and it would express the final answer in terms of moles solute. So molarity itself is a conversion factor. You have to sort of unpack it a bit, where 0.20 there for every liter, if you see that M sign, then for every liter there are that many moles. So for every 1 liter there are 0.20 moles of solute. And if you were to calculate this, you know, your milliliters would cancel out, your milliliters would cancel out, and of course your liters would cancel out, and you'd just be left with moles solute. So 500, right, times 0.20. If you take the whole quantity and you essentially divide it by 1,000, then you'd get 0.1, right? So you have 0.1 moles of HCl in either solution, right? I mean, the mole amount really doesn't change as we add more water. In other words, as we dilute the solution in its totality, it doesn't really change the amount of moles. So had we had the amount of milliliters that are contained within this container that has this particular molarity, we would get the same amount of moles. So this is helpful, right? I mean, this is helpful. We now know how many moles there are in this particular, in HCl. We know that there are 0.1 moles. And of course, leveraging the fact that both containers will contain the same amount of moles, we also know that this guy has 0.1 moles. So now we can plug this information into the formula that we were originally trying to plug information to, which gives us our molarity, but it can also give us, like I said before, one of the 3 things, right? So we know the molarity, right? And we know moles solute, and now we can just solve for liters, which is of course what we were trying to do in the original question, or that is of course part A. So the idea now is to then take the fact that you know how many moles are in the first solution, right? Moles solute, or in other words, HCl. I mean, when I say solute, I'm really referring to HCl. And then, of course, divide by liters solution, which is, of course, what we're trying to solve for. So we could just leave that as liter solution. And then, of course, what we'll do is we will equate that to our molarity, which we know to be 0.8 in terms of its molarity, and then we'll solve for X liters. In the process of doing so, of course, you would multiply both sides by X liters, and your X liters would cancel out, and you'd be left with this. And then, of course, to isolate X liters in order to equate it to something that has an identity, we would then, of course, say 0.1 moles solute. In other words, we would just divide both sides by 0.8 equals X amount of liters. And so if you were to do this, if you were to sort of plug this into a calculator, 0.1 in terms of moles, and of course 0.8 in terms of molarity, you would get 0.125 liters of course, because like I said before, the molarity formula expresses the quantity in terms of liters if you were to solve for liters or if you were to plug in. And so that's your answer. I mean, you know how many liters are in this particular container here. But the idea is we want to know, if you wanted to know how, just because everything in the question is sort of expressed in terms of milliliters, if you wanted to know how many liters that would, or milliliters that would be from liters, you would essentially multiply it by 1,000, knowing that 0.25 liters, if you were to have a conversion factor, you know that 1 liter is equal to 1,000 milliliters. So ultimately you'd end up multiplying both quantities, and then of course you'd get 125 milliliters in the original quantity. Now this brings up a very important point that I would like to sort of bring up. And the point is that, what you could have done, is you could have said that instead of having gone this route, you could have, let's see here. So, so what you could have done, I mean, there are lots of things that you could have done that would have been sort of wrong. And I want to sort of highlight those things. In calculating the moles, right? You know that you had to calculate the amount of moles. So if you were, sort of rewind a bit, if you were again finding yourself in this position where we were calculating the moles in both of these compounds, knowing that the mole amount would be the same for both, you couldn't start, we had a starting point from 500 milliliters, right? And then we worked our way, as I said here, we worked our way to the amount of moles, but we couldn't have started with this guy because we didn't know how many milliliters that was or how many liters that was. So while we knew basically while we knew the volume for the second quantity or the second solution, but we didn't know the quantity for the first solution, which is why, if it's not intuitive that we started with this guy, then that's essentially the reason why. And then moving on to the second part, when you were plugging in everything, you could have, what you could have done, you could have said, okay, you have mole solute, right? You have 0.1 moles of HCl, which is your solute, and you're solving for X amount of liters. And then you equated that to a molarity. Now, you're given two molarities here. You're given 0.20 and you're given, 500 milliliters. I mean, sorry, 0.8 molarity. So you're given two molarities, 0.8 and 0.20. If you would have represented your molarity as 0.20, I mean, why couldn't we do that, right? Well, the molarity, you would get the wrong answer, obviously, because the molarity of 0.20 essentially corresponds to this particular solution. So if you were to solve for liters in this case, you would essentially get the volume in liters of this guy, right? Not this guy. You wouldn't get it of this guy. You would get it of this guy. And that's because you're corresponding your moles, which were in this container, to your molarity of this container. So here we use 0.8 molarity because we knew that the molarity corresponds to this container. That's the volume that we wanted to solve for. So if you were to do this, right, if you were to divide both sides by XL and then cross that out, and then of course say that XL equals 0.20 molarity, or actually you would have to say 0.1 divided by 0.20. Let's see what that would give us. Let's see here. You could see that you would get 0.5 in terms of liters. And if you were to multiply that by 1,000 to get milliliters, you would get 500 milliliters. And you already know that your second container has 500 milliliters. So it would just pop out the solution volume of the second container, not the first. So it's really important to be able to group information in terms of what is for what solution, right? 0.8 molar solution was for this container. 0.20 molar solution is for this container. 500 milliliters is for this container. And of course, when you get your final answer, which is 125 milliliters, that is for this container. So it's really important to group information in that manner, and drawing a picture really helps that purpose. But of course, part B says how much water was added to make this happen. Well, you know now that the original solution has a milliliter quantity of 125. And then of course you added 500 milliliters, which of course is apparent in the question. So how much you added in terms of in terms of the whole amount, you didn't add 500 milliliters, but you added an X amount of milliliters, which brought you to 500 milliliters. So you just, to find the difference really would just be 500 minus 125, which is 375. So 375 milliliters was added in order to get you there.